In the last lecture, I introduced transistors. In this lecture, I will explain how transistor works. I also explained the meaning of name BJT. BJT. B stands for bipolar. B stands for bipolar. We have bipolar in the name because there is involvement of both type of charge carriers. There is involvement of electrons as well as holes in transistor. That's why we have bipolar in the name. J stands for junction. J stands for junction. Two junctions are formed in transistor, junction J1 and junction J2. Two junctions are formed in transistor, so we have junction in the name. Now the most important thing is the meaning of transistor. Why we call this three-terminal device transistor? The name transistor is coined from word transferred resistor. Transistor is coined from transferred resistor, in which we have trans and istor, I-S-T-O-R, and this two makes the word transistor. Now what is the meaning of transferred resistor? If we talk about active mode, of operation, then we already know junction J1 is forward biased and junction J2 is reverse biased. When junction J1 is forward biased, it will offer a very low resistance, or ideally resistance should be 0. When junction J2 is reverse biased, it will offer a very high resistance, or ideally the resistance must be infinity. So this is what we have in active mode, and if we have same current flowing, then initially it will flow through a low resistance. Let's say the current is I, and after this at output it will flow through a high resistance. Let's say it is capital R, and the same current is flowing through both these resistances. So somehow we have transferred the low resistance to the high resistance. That's why we have the name transferred resistor, and from this we got transistor. There is very significant use of this thing. For example, let's say VI is the input voltage and VO is the output voltage. We are measuring VI across this small resistance, and we are measuring VO across this large resistance. So VI is equal to I multiplied by R, and VO is equal to I multiplied by capital R. The current is same and the input resistance is smaller than the output resistance, so we can say that VI is smaller than VO. So we had a weak signal at the input, but we have an amplified signal at the output. So there is amplification by using the three-terminal device. All these things will be clear when I explain the working of NPN transistor in active mode. This is NPN transistor. So the emitter region is N, the base region is P, and the collector region is N. This is NPN transistor. This terminal is emitter terminal, this terminal is base terminal, and this terminal here is collector terminal. And we want to operate this transistor in active mode. We want to operate this transistor in active mode, and we already know in active mode junction J1 is forward bias. So to forward bias junction J1, we need to apply a forward bias potential. N is connected to the negative terminal and P is connected to the positive terminal. So emitter is connected to the negative terminal and base is connected to the positive terminal. Let's say this forward biasing potential is VEB, and we have to reverse bias junction J2. So N is connected to the positive terminal and P is connected to the negative terminal. Collector is connected to the positive terminal, base is connected to the negative terminal, and let's say this reverse biasing potential is VCB. Now we have junction J1 forward biased and junction J2 reverse biased. Now we will analyze the movement of electrons and holes in this three-terminal device, and let's say VB is the barrier potential for junction J1 and junction J2. when the transistor terminals are open circuited, there is no biasing potential in the transistor. So VB is the barrier potential for junction J1 and junction J2 when there is no biasing potential, and we have to analyze what will happen to the barrier potential once we apply the biasing potentials in the transistor. This is barrier potential of junction J2 and it is equal to VB. This is barrier potential of junction J1 and it is also equal to VB. Now junction J1 is forward biased after the application of VEB, and the barrier potential will now reduce, and let's say the new barrier potential is this. The new barrier potential is equal to VB minus VEB, forward biasing potential. On the other hand, junction J2 is reverse biased, so barrier potential will increase, and the new barrier potential is equal to VB plus VCB, the reverse biasing potential. Now we can easily analyze the movement of electrons and holes because we have idea about the barrier potentials. Because of the reduced barrier potential at junction J1, the electrons on the N side, that is the emitter, will cross the junction and move to the base and recombine with the holes in the base. There is one very important thing that you always have to keep in your mind. Base in case of transistor is very small, and it is also lightly doped. And because of this, because base is thin and it is lightly doped, there is very small recombination of electrons from the emitter, and most of the electrons from the emitter pass over to the collector. I will repeat this point again. Barrier potential at junction J1 is reduced, so electrons from emitter will cross over the junction, and very small amount of electrons from the emitter will recombine in the base because base is very small, very thin, and it is lightly doped. So most of the electrons will cross the junction J2 because they have high velocity, and this implies they have high kinetic energy. So most of the electrons emitted by the emitter will find themselves in the collector. A very few electrons will recombine with the holes, and this means electrons will move to VEB, the positive terminal of the forward biasing potential. Let's say n number of electrons enter the base, out of which 1 minus alpha n electrons combine with the holes in the base, and alpha n electrons move to the collector. This is what is happening in the transistor. Only 2 to 5% electrons are combined in the base, and 95 to 98% electrons are collected in the collector. Therefore, most of the electrons emitted by the emitter move to the collector. So this is what will happen when you forward bias the junction J1 and junction J2 in bipolar junction transistor. There is one more thing that we must not forget, and it is the reverse saturation current. Junction J2 is reverse biased, so there must be reverse saturation current through junction J2. We have minority charge carriers on N side and we have minority charge carriers on P side. On N side, minority charge carrier is hole. On P side, minority charge carrier is electron. So this hole will move like this and this electron will move like this. So there is current called as reverse saturation current or leakage current when the junction J2 is reverse biased. I am calling the reverse saturation current or leakage current ICO, because this current is associated with the collector. So there is subscript C. This O stands for open circuit. We measure this current when emitter terminal is open circuited. So this is why I am calling this current ICO. And if I want to find out the collector current IC, then it is equal to alpha IE, alpha times the ammeter current, because N is the number of electrons entering the base and alpha N is the number of electrons moving to the collector. So current will be alpha times IE plus ICO. So this is the value of collector current. The next thing is to find out relation between the ammeter current, base current and collector current. For this purpose, first we have to find out direction of the three currents. You can see electron is moving from left to right, so direction of current is like this, from right to left. This is IE, the ammeter current. When electrons from ammeter recombine with the holes, the direction of current will be like this, and the current is IB, because electron will move in this direction to the positive terminal of the battery, so current will flow in opposite direction. And to find out collector current, we again have to focus on the movement of electrons. Electrons are moving from base to collector like this, in this fashion. So current will be like this, from right to left. And to find out relation between IE, IB and IC, we have to use Kirchhoff's current law, KCL. And from KCL we know sum of currents entering is equal to the sum of currents leaving. IE is leaving, IB and IC are entering, so IE is equal to IB plus IC. This is what we have in the NPN transistor in active mode. These two relations are very important, and we will talk more about alpha in the coming presentations. This is all for this lecture. See you in the next one.